So we are very happy to have Sarah Peluse speaking this week, and she will be talking about modular zeros in the character table of Sn.
Right, so thanks for the invitation to speak. So I'll start by recalling some really basic definitions and results from representation theory. In this whole talk, all representations will be complex representations. And topic of this talk are the characters of the symmetric group. And so we'll let G be a group and define the characters of representations of G. So if rho is representation, we define its character chi sub rho, which is a function from G to complex numbers, by just taking the trace of the representation evaluated at G. So the character of representation uniquely determines it up to isomorphism. So characters just by the orthogonality relation for characters. You can just read off the irreducible representations that appear in your representation if you know the characters. And characters are class functions. Meaning that they're constant conjugacy classes. And the number of conjugacy classes of A group G equals the number of irreducible representations. Which for the remainder of the talk, I'll abbreviate by irreps of the group G. So this means we can organize all of the data of the characters of our group in a character table, which is a square table, where let's say we label the columns by the conjugacy classes. And the rows by the irreducible representations. And then where a column meets a row, we'll put the value of that irreducible representation or of the character corresponding to irreducible representation at the conjugacy class. So in the specific case that we care about in this talk, where G is the symmetric group on n letters, the conjugacy classes are in one-to-one correspondence with partitions of n. So it's probably not necessary for me to define partitions for this audience, but I will anyway. So partitions of n, meaning decreasing sequences of positive integers that sum to n. And the correspondence is, so a conjugacy class of permutations is determined by the cycle type of those permutations. So you just take the lengths of all the cycles appearing, and that gives you a partition of n. There's also a natural correspondence between irreducible representations of Sn and partitions of n. This is a very beautiful correspondence, but I won't have time to describe it to you. And so we'll denote the character values of the symmetric group So of the character of the representation corresponding to a partition lambda, evaluated the conjugate class corresponding to a partition mu by chi sup lambda sub mu for the remainder of this talk. Okay, so here's an example of a character table of a symmetric group, so of S5. So I've kind of labeled the conjugacy classes with the corresponding partitions Young diagram, and the same with the irreducible representations. So this first column is the identity permutation. So this gives you the dimension of the irreducible representation, or the degree of the character. And we have all the other columns. And kind of one important thing to note is that all of these integers, or all of these entries appearing, are integers. And this is kind of a special property. Like this is not true for like most character tables of like finite groups. So for example, if you take any like abelian group, or any abelian group that's not like Z2 to some power, then you're definitely not going to get all integers in the character table. And this turns out to be something that's generally true about all symmetric groups. So it is a fact that for all n, chi sub mu sup lambda is always an integer. Okay, so the characters of a finite group are kind of very important and fundamental object of study. They come up all the time in like combinatorics and group theory. And now for each of these like really important algebraic objects, we have some collection of integers that correspond to them. And so then it's natural, if you're a number theorist, to ask like, what are the statistical properties of these integers? Like how often are they zero? Are like half positive and half negative? Like how often are they even? So Alex Miller investigated these questions computationally. So he computed the character values or I should say values of Sn mod 2 for all n up to 78. And he noticed that the proportion of even entries seem to be converging to 1. So it looked like as n grew, like almost every entry of the character table of Sn was even. And so somehow, even though people have been interested in the character tables of symmetric group and like interested in computing them for like decades, somehow I guess Alex was the first one to notice this like kind of beautiful thing. And so based on this, he conjectured that yes, as n goes to infinity, the proportion of odd entries in the character table of Sn goes to 0. So there was, I guess, There's a tiny bit of work related to this before Alex made his conjecture. So it's been known for a long time, the work of McKay, that the degrees of irreducible representations are almost always even. So that first column of the character table is almost always even. And you actually write down like an exact formula for the number of characters of odd degree. And then after Alex made his conjecture, there's some partial progress towards it due to Gluck and Marodi. But kind of these taken together don't show that even a positive proportion of the character values of Sn are even. So one of the results I'll be speaking about today is a proof of Miller's conjecture for even entries in the character table. So indeed, the proportion of odd entries in the character table of Sn goes to 0. Oops. As n grows. Okay, so Alex looked at some more statistical properties of these character values. So he also computed the full character table, not just mod 2. For all n up to 38. And he noticed similarly that even though it wasn't, kind of converging as fast, that the proportion is for any fixed prime p. I guess he noticed it for p equals 3 and 5 as well. The proportion of entries not divisible by p seemed to also be going to 0 as n grew. So based on this, he conjectured more generally that as n goes to infinity, the proportion of character values of Sn not divisible by p goes to 0. And fairly recently, Sound and I were able to prove this more general conjecture. And actually with a degree of uniformity in the primes, p. So we let n be a larger than some absolute constant. Also let p be any prime that's a bit smaller than log n. So like log n over log n, log n squared. Then the density of entries in the character table of Sn not divisible by p is big O of n to the negative 1 over 12p. So this says that almost every entry of the character table of Sn is visible by kind of all small primes. So before I start talking about the proofs of these two theorems, I guess I'll pause for questions. Okay, so if there are no questions, I'll continue. So the proofs of these two theorems and are based off of the same two key lemmas. So we'll need two key lemmas. So the first I'll call the large part lemma. So I'll kind of write it down and then I'll tell you just intuitively what it's saying. So we'll let L be some parameter. It's smaller than log n over log n. And suppose that mu is a partition of n with largest part of size at least 1 over 1 plus 1 over L times square root of 6 over 2 pi times square root of n log n. So then the proportion of partitions lambda of n, for which the character value chi lambda mu is not 0, is at most big O of log n over n to the 1 over 2L. Okay, so for context, Erdish and Lehner, I think in the 30s, showed that a typical partition of n, so just chosen uniformly at random, has largest part close to square root of 6 over 2 pi times the square root of n log n. So the mu in the large part lemma have largest part kind of significantly larger than the kind of expected largest part of a random partition. So what the large part lemma says is that if mu has some kind of strangely large part, then most irreducible characters evaluated at the conjecture class corresponding to mu are 0. So most entries in the column corresponding to mu in the character table are 0. So how is this proved? It's for the people who have some background in the representation theory of symmetric group. So it follows from the Murnaghan-Nakayama rule that if mu has a part of size t and lambda is a t-core partition, then the character value chi lambda mu is 0. Large part lemma then follows by just kind of getting a lower bound for the number of t-core partitions when t is large. So a bit larger than the expected largest part of a random partition. It just follows by lower bounds for the number of t-cores. So this is the first key lemma. Second, I'll call the combining parts lemma. So we'll fix a prime p. And now for the rest of this talk, every time p appears, it's going to be prime. Now suppose that mu is a partition of n, and that nu is another partition of n that's obtained from our first partition mu by replacing any p parts of the same size m in mu with one part of size p times m. So we've combined these p parts together into one big part. So then the lemma says that for all partitions lambda of n, the character values of mu and nu are congruent mod p. So if you have some partition mu and you get another partition nu that's obtained by combining any p parts of the same size in mu, then the columns of the character table corresponding to these two partitions are congruent mod p. So here's an example of this combining parts operation. So, so let's say p is 2. Then the character values for partition 2, 6, 1, 1, 1, mod 2. It's congruent to the character values for 6, 2, 2, 1. So I've combined two parts of size 1 into one part of size 2. And then I can also combine these two parts of size 2 into one part of size 4. So this is true for all lambda partitions of whatever this adds up to 11. So all these character values are the same mod 2. So, okay, how is this proved? So this is this just follows from Frobenius's formula for characters. So what you do is you just reduce the polynomials appearing in Frobenius's formula. Modulo p. And you see that the kind of polynomials in Frobenius's formula for computing the character values for mu and nu are just congruent mod p. And then this shows that the character values themselves are congruent mod p. So now with these two lemmas, I can describe to you the kind of overarching strategy of the proofs.
Sarah, we have a quick question in the chat.
Oh yeah.
Asked if the operation has to be performed on all parts appearing p or more times, or can it be taken in steps?
It can be taken in steps. Yeah.
That's very interesting. Then that's it sounds like that works really well with Glacier's map on partitions, which is exactly that process for when you take partitions into odd parts and you map them exactly to partitions into distinct parts. You can group things two at a time, and you can do that for other moduli as well. So that's really interesting, actually. I kind of wonder if there's a connection between that map and this operation.
Oh, so I've never heard of this operation. So what's it called again?
So this is one of the fundamental maps in partition theory. It's called Glacier's map.
Like glacier, like the
Glaisher. And
Okay.
so it's a combinatorial map between the first one that you see is the map from partitions with distinct parts to partitions with odd parts, or vice versa. So you take any two odd parts of the same size, you replace them with a part of size 2m. And if you repeatedly do that until there are no repeated parts, you get a partition into distinct parts. And of course, you can unwind that as well. So it's a bijection between the two set. You can also do this mod m for any other modulus. Doesn't have to be prime as well either. I presume this probably doesn't apply when the modulus is not prime. But at any rate, this is exactly what is being done here. So you might be able to take that map and this lemma, and maybe you can make some statements about other distributions as well. I didn't want to jump into your talk, but the connection sounded interesting. I wanted to ask about that. Thank you.
Oh, no, thanks. This is really interesting. I'm not really a partitions person, so any sort of like reference to other things that this is connected to is like interesting to me. So
yeah, like
I'll look into this.
See if there's any, maybe any synergy there.
Yeah, it's good to know that at least for PS2, this has a name. Okay, awesome.
Sure.
Thanks. So now I'll try and describe the kind of idea of the two proofs. Okay, so let's fix prime P. Then for any partition mu of n. So we actually do kind of what was just described. So repeatedly apply this combining parts lemma until there are no parts appearing more than p minus 1 times, or more than, more than p minus 1 times. So for any partition mu, we let mu tilde denote the partition of n obtained by repeatedly replacing any p parts of the same size with a part of size p times m until no parts appear more than p minus 1 times. So do this operation until you can't do it anymore. So for example, same one from the previous slide. If p is 2 and mu is the partition 6, 2, 1, 1, 1, then mu tilde is 6, 4, 1. So here's the idea of the proofs. So the combining parts lemma implies that character values for mu are congruent to the character values mu tilde mod p for all lambda and mu. So to show that almost every character value is 0 mod p, it suffices to show that for almost every pair of partitions lambda and mu, the carried value for lambda and mu tilde is 0. So by the large part lemma, is that then it suffices to show for typical mu tilde has a large part. Right? Because then for most lambda, the character value chi lambda mu tilde will be 0. So then the character value chi lambda mu will be 0 mod p. And kind of showing that for almost every mu tilde has a part significantly larger than the expected largest part size for a random partition. So showing this is the kind of heart of the argument. So now I'll describe how we show that. So we do it by following partition statistic. So we define it for any integer k that's relatively prime to p, and any partition mu event. We find capital M sup k sub mu to be the size or the sum of all parts of mu of the form k times a power of p. So I don't know if this has been cited before or if it has a name. I'd be grateful to hear if it has. So for example, again, when p equals 2, then when k equals 1, this thing for the partition 6, 2, 1, 1, 1 equals 5, because we sum up 2 plus 1 plus 1 plus 1, all the powers of 2 appearing there. And note that this is the same as the corresponding value for mu tilde of our original partition 6, 2, 1, 1, 1. And it's not hard to see that in general, the statistic, maybe I should put that below. Statistic is the same for mu and mu tilde. And kind of further, you can read off the parts of the form k times a power of p that appear in mu tilde just from the base p expansion of capital M sub mu. So kind of more precisely, the base p expansion of 1 over k times this quantity has an I in the p to the j place if and only if mu tilde has I parts of size k times p to the j. So depending on kind of what the image or what the fractional part of log k to base p is, showing that mu tilde has some large part kind of boils down to showing that this partition statistic is large for some k. So to be more precise, to show that mu tilde has a large part. So by large, I mean that a part of size a little bit larger than the expected largest part of a random partition. Suffices to show that the floor of the log of this quantity is at least this large. So kind of for suitable k, you basically just want to show that this capital M statistic is basically just a bit larger than this expected size of the largest part in a random partition. Okay, so how do you show that? So we want to show so we want to show this, sorry, for some k. We just need to show it for 1k. So now things boil down to showing that the statistic is typically large. So the strategy is different when p is 2 versus when p is a larger prime. So it turns out that this statistic for fixed k has average size about 1 over log p times expected largest part size. And then the difference between p equals 2 and p is greater than 2 is that 1 over log 2 is actually greater than 1. So to show that the statistic is typically large, you just have to show it is typically close to its average size. And this turns out to be really not that hard. So the generating functions for the moments are easy to write down. And also nice. So you can just kind of do some like a very easy stationary phase argument to write down like just the first 2 moments, and then you can use Chebyshev's inequality to show that these statistics are typically close to their average, which is large, so they're typically large. So then just have to estimate moments and use, say, Chebyshev's inequality. So that kind of completes the proof of Miller's conjecture for the prime 2. So when P is greater than 2, 1 over log P is less than 1. This capital M K mu actually turns out to be typically small for each fixed K. So then you need to consider kind of multiple K at a time, and then show that even though individually the statistic is small for each K, it can't be small for all of them. So kind of one way to argue is to show that the capital M statistic is independent for sufficiently many Ks. But turns out you can only show this for about n to the 1/4 many of these Ks at a time. And it turns out you kind of need more Ks to possibly make this like independence argument work. So using that sort of argument, you can only prove Miller's conjecture for primes up to and including 13. So then to go past this, Sound and I just consider directly the generating function for number of partitions mu with mu tilde having no large part. So you can write this down. Let's call it, I don't know, FQ. So then you can just estimate the number of partitions that don't have largest part by bounding, or not estimate, but upper bound for some well-chosen real number R, 1 over R to the n times this generating function evaluated at R. We kind of just do this, and it's not that bad. And then this shows that most mu have mu tilde having large part. So that completes the proof of our theorems that almost every entry of the character table of Sn is divisible by any fixed prime, because we've shown that for random mu tilde has some large part. So most character values for mu tilde are 0. And so for almost every lambda and mu, there are partitions of n, the character value is 0 mod p. So to finish, I'd like to highlight some open questions related to this. So Alex Miller in his paper have also looks at other statistical properties of the character values. So he also has data suggesting that almost every character value should be a multiple of any fixed prime power. So then showing this, it would then follow that for any fixed integer, almost every character value is divisible by that integer. So our argument doesn't say anything about higher powers because this combining parts lemma isn't true anymore. So we don't know what to do there. And Miller also, so he also has data suggesting that about half of the non-zero character values are positive, another half are negative. So I have no idea how to approach this or even how to start. And I think most interesting of all is the apparently much older, as I've heard from people, open question of just how many character values of a symmetric group are zero. Just how many in the character table are zero. So it's not even known if a positive proportion are. So not much is known. So from Alex's computations, so we know that a 0.3659 proportion of entries in the character table of S38 are zero. But it's kind of very computationally difficult to get data for much larger n. It's hard to tell whether it's kind of approaching some like asymptote or it's just decreasing like 1 over like log or log or something. So from the large part lemma and Erdős and Lehner's work, it follows that at least 1 over log n proportion of zeros. So at least a 1 over log proportion of entries are zero. I think this is kind of the best lower bound that's known for the number of zeros. And finally, I'll mention that there are results for other groups kind of in related settings. So Larson and Miller last summer showed that so almost every entry of the character table is zero for finite simple groups of Lie type in the large rank regime. So as the rank goes to infinity, the proportion of zeros in the character table of any finite simple group of Lie type the portion of zero entries goes to 1. And okay, it's 12:50. Okay, at least for me. So I think I'll stop here.
Great. Let's thank Sarah for her talk. And then I guess let's open the floor. Does anyone have any questions? I have, I guess, a question. I kind of related to the last bullet point you said. I was going to ask if there are any similar results to what you've proved for any other families of groups. And so, like, I'm not sure exactly how to phrase this because, right, SN is so nice because all of the entries are integers. Like, my first instinct was to ask about the alternating groups, but you have to be careful of exactly what fields those entries lie in. I don't think it doesn't stabilize nicely, I guess. But is there maybe some, like you had a result about primes growing, or the primes dividing entries as n grows or something like that? Do you have any suspicion of like if something like that is true for alternating groups or anything else?
So people have asked me about the alternating group before, and I kind of fortunately haven't like thought about it after they asked me. Maybe I should think about it. So I guess you could look at like the entries that are actually integers
You
and
should,
ask.
I mean, even like entry primes and other rings of integers or something like that.
Oh, that's a good idea. No, we haven't thought about that. Yeah, maybe I'll email Sound.
Yeah, I mean, there's a nice there's a nice result for John Thompson proved like right exactly what fields you get as n grows for the alternating groups. So you should be able to actually pin down for like any finite n what the right question is. I don't know exactly how to ask that. It's like n goes to infinity though.
Oh, that's a really good question. I'll think about it.
I mean, you know, the entries are algebraic integers. It still makes sense to ask whether an algebraic integer is even or not. So you might not even have to know the exact field.
It's true. Yeah, I mean, yeah, and obviously like, the questions about being zero make sense. Always. Any other questions?
I have a comment.
Okay.
It's a numerological comment about S38. So 0.3659 is extremely close to 1 over E.
Oh yeah, yeah.
And 1 over E has to do with the derangements of random permutations. So that could be a coincidence or it could be a clue.
Any other questions or comments for Sarah? Great. If not, let's thank Sarah again.